We will discuss fate and transport concepts of total petroleum hydrocarbon, or TPH. First, we'll discuss how TPH can be chemically transformed in the environment, which is also called environmental fate. TPH fate can be driven by biological weathering and how weathering changes the compounds that make up the TPH mixture while creating petroleum metabolites in the process. Secondly, we'll discuss transport of TPH once it enters the environment and migrates from one medium to another, which is called partitioning, ultimately ending up in an exposure media such as groundwater or indoor air. Once TPH migrates from the source to an exposure media, a person may contact TPH by ingesting groundwater or breathing indoor air, for example. Therefore, when conducting a proper site investigation, it is really important to understand TPH fate and transport. Biologic weathering, also called biodegradation, is a major contributor to TPH hydrocarbon mass reduction in the environment. In addition, biodegradation generates petroleum metabolites that can be further degraded in a stepwise process. Because biodegradation requires microorganisms and adequate oxygen to support microorganisms' respiration, it makes sense that biodegradation rates depend on how much oxygen is available. If microorganisms have plenty of oxygen to support their respiration, they will biodegrade TPH faster versus microorganisms with limited or no oxygen present, which not only slows the rate of biodegradation, but also produces methane and more petroleum metabolites, which will require further biodegradation. Because biodegradation occurs as a multi-step process, NAPL tends to take longer to degrade than vapor or dissolved phases. Why is this the case? Simply put, there is more mass in NAPL to biodegrade, which requires more oxygen versus vapor or dissolved phases. As you can see, the top graph shows unweathered diesel, which is easily recognized by the N-alkane picket fence pattern. The bottom graph shows the same diesel after it's weathered. The first thing you'll notice is that the picket fence is gone for the most part because these straight chain N-alkanes are easily biodegraded. What remains is the hump, which is made up of an unresolved complex mixture, or UCM for short. This hump is mainly highly branched alkanes that are more resistant to biodegradation than N-alkanes, although highly branched alkanes do ultimately biodegrade. To conceptualize some of these fate and transport processes, I thought it would be fun to provide some cartoon animations. As you can see in this animation, the poor hydrocarbon is being biodegraded by the hungry microorganisms, and in the process, generating petroleum metabolites, which are shown as M's. Petroleum metabolites, which are also called polar metabolites, are intermediate products of biodegradation, which gives them some unique chemical properties. To begin with, petroleum metabolites include oxygen, which makes them polar. Basically, this means the electrons are not equally shared, which causes petroleum metabolites to preferentially partition into water, making them very soluble and mobile in water. The table illustrates differences in solubilities and boiling points of N-hexane versus its petroleum metabolites 2-hexanone and hexanoic acid. As you can see, N-hexane's solubility limit is 3 orders of magnitude lower than its petroleum metabolites. The result of this is shown in the bottom right graphic, where petroleum metabolites have migrated further in groundwater versus dissolved phase hydrocarbons like BTEX or free phase NAPL. Don't bet against petroleum metabolites wearing the red M in a swim meet because they move faster than dissolved phase hydrocarbons. Metabolites are primarily measured via extractable TPH bulk analysis for TPH diesel or TPH motor oil, for example, when silica gel cleanup, or SGC, is not used because silica gel removes the metabolites from the sample. Therefore, identifying whether metabolites are present at your site involves using a multiple lines of evidence approach. The first line of evidence is whether a metabolite hump is present in the chromatogram pattern as shown in the graph. The second line of evidence is whether chemical analyses have been performed with and without silica gel cleanup on the sample. If the analysis without silica gel cleanup shows detected concentrations of TPH, while the silica gel cleanup analysis shows no detectable concentrations of TPH, it is likely that the detected TPH is comprised of metabolites. The third line of evidence is the nature and extent of TPH, essentially asking if the sample in question was collected down gradient of both the release area and the dissolved extent in groundwater. This is illustrated in the hypothetical site map, showing an NAPL release in dark orange, down gradient migration of dissolved hydrocarbons, including BTEX, in light orange, and further down gradient migration of petroleum metabolites, shown as polars, in blue. Again, the petroleum metabolites travel further because they are polar, which makes them much more soluble and mobile than dissolved hydrocarbon, aromatic, or aliphatics. It's interesting to note that toxicity factors developed for petroleum metabolites tend to be lower than the toxicity factors assigned to the undegraded hydrocarbons. Another way to illustrate TPH's environmental fate in groundwater is presented on this slide. As you can see, the release area is located on the right side of the top graphic, with groundwater flow to the left. Beyond the release area, TPH's groundwater plume is cigar-shaped as shown, or it may occur as thin bands around NAPL or heavily impacted media. The length of the groundwater plume tends to be a few hundred feet in general, and the TPH composition can change along the flow path due to transport and sorption properties of TPH compounds, biodegradation rates of TPH compounds, and different redox zones in the subsurface. Basically, more oxygen is present in the subsurface to support biodegradation. In the top graphic, anaerobic conditions exist within the plume boundary, while aerobic conditions are limited to the plume boundary and beyond, where aerobic respiration can occur. The bottom graphic illustrates the same release and groundwater flow, focusing on the relative concentrations of dissolved hydrocarbons, which are shown in blue, versus petroleum metabolites, which are shown in orange. In general, concentrations of dissolved hydrocarbons are highest near the source and diminish as they move down gradient away from the release, which makes sense. On the other hand, since petroleum metabolites are a product of biodegradation, their maximum concentrations occur down gradient of the source. Once present in groundwater, metabolites will migrate further down gradient than dissolved hydrocarbons due to their increased solubility and mobility. Over time, metabolite concentrations may increase near the source, essentially shifting the apex of the triangle to the right as long as there is still source mass to biodegrade. Now that we understand TPH fate, let's dive into how TPH partitions in the environment. It's really important to understand how TPH moves in the environment from source to exposure media. First up, we'll discuss how hydrocarbons partition from oil into vapor through volatilization. In general, smaller hydrocarbons are more volatile than larger hydrocarbons. Therefore, the vapor phase is dominated by these smaller aliphatic and aromatic hydrocarbons. If we were to plot boiling point on the x-axis and vapor pressure on the y-axis, we would see a single curve identifying those hydrocarbons with the greatest volatilization potential as those with the higher vapor pressures and lower boiling points. These hydrocarbons are circled in blue. It makes sense that these hydrocarbons would volatilize easily and end up in the vapor phase. EPA considers a chemical volatile if its vapor pressure is greater than or equal to 1 millimeter of mercury, which is the purple line on the graph. Notice that when vapor pressure drops and boiling point increases, there is more scatter on the graph, which is due to difficulty in measuring these compounds. Our smaller and lighter hydrocarbon is showing off his volatilization skills, while the larger hydrocarbon attempts to volatilize, but is just too heavy. Now let's look at how hydrocarbons partition from oil into water through dissolution. If we were to plot boiling point on the x-axis and solubility limit on the y-axis, we would see that, like volatility, smaller hydrocarbons are more soluble than larger hydrocarbons. However, there are differences based on the compound's chemical class. In the TPH general chemistry video, we talked about two classes of TPH compounds, aliphatics and aromatics. Aliphatics can occur as straight or branched chains and non-aromatic rings, while aromatics typically contain at least one benzene ring. In general, aromatics are more water-soluble than aliphatics. Therefore, the composition of the TPH water-soluble fraction is dominated by aromatics. Aromatics are represented with blue dots and the blue trend line on the graph. Given the same boiling point, the solubility limits of aromatics can be several orders of magnitude greater than aliphatic solubility limits, which are represented with green dots and green trend line on the graph. Now that we understand how TPH partitions in the environment, let's discuss ways we can measure TPH in the environment. In addition to differentiating between aromatics and aliphatics, identifying TPH fractions within these chemical classes is helpful when looking at TPH compositional changes and inferences about TPH risk. TPH fractions are essentially groups of hydrocarbons with similar characteristics. The use of a TPH fraction approach with fractionation methods is essential when assessing TPH risk because the approach provides accurate hydrocarbon quantitation aligned with toxicity values and physical-chemical parameters. It's helpful to think in terms of TPH fractions, similar groups of hydrocarbons, for both composition and risk. Two fraction approaches are shown on this slide, where each block is a fraction and the x-axis is the equivalent carbon, which increases in size from left to right. The y-axis includes two rows showing aliphatics on the top in green and aromatics on the bottom in blue. The first TPH fraction approach is based on transport fractions identified by the TPH criteria working group. Essentially, these consist of 13 transport fractions. Note that the 14th fraction, high boiling aliphatics, is not considered mobile. Starting from the left, each successively larger carbon fraction has transport properties that are about an order of a magnitude less volatile and less soluble. By mid-diagram, the fractions are about 4 orders of magnitude less volatile and less soluble than those on the far left. The second TPH fraction approach is based on toxicity fractions identified by EPA. As you may notice, there are only 6 large blocks in this approach, which is due to limited availability of toxicity data for each fraction. To simplify our discussions going forward, we will only present EPA's toxicity fractions, called low, medium, and high, for aliphatics and aromatics in order to illustrate TPH composition changes. The next 4 slides present TPH fraction compositions, which vary based on the oil-fuel mixture and weathering processes. On this slide, we start with the basics, NAPL composition. This slide presents graphs of TPH fraction compositions for 3 different unweathered NAPL mixtures, gasoline, diesel, and motor oil. The x-axis shows the presence of the 6 fractions in increasing equivalent carbon number, low, medium, and high. Colors differentiate the 2 hydrocarbon classes, in which aliphatics are shown in green and aromatics are shown in blue. The y-axis is the proportion with a maximum value of 1. For each graph, the total fraction proportions are 1 or 100% by weight. Take a moment to compare the different unweathered NAPL mixtures to understand how their compositions vary. For example, it makes sense that unweathered motor oil is mostly comprised, 76% to be exact, of high or heavy aliphatics, and the remainder is comprised of high aromatics. You wouldn't expect to see lighter aromatics or aliphatics in motor oil, but you would expect to see these lighter fractions in unweathered gasoline. The fraction composition of NAPL is an important concept to understand when characterizing risk. Now that you've committed the unweathered NAPL graphs to memory from the last slide, I'm joking of course, we'll compare examples of fresh and weathered fuels released at a hypothetical site. Let's focus on gasoline first. As you may recall from our partitioning graphs, smaller hydrocarbons are the most volatile and soluble constituents. Therefore, it makes sense that when gasoline weathers, the smaller, lighter fractions would be first to partition into air and water. As a result, these low fractions are completely depleted in the weathered gasoline. Now that you're getting the hang of it, let's look at the diesel graphs and see how weathering changes its composition. Again, not a surprise that the biggest change is the depletion in medium aliphatics and aromatics. What if we compare the relative proportional shifts between gasoline and diesel? The weathered diesel example doesn't quite show as much depletion as the weathered gasoline example, but it does illustrate the overall shift to proportionally heavier fractions. Okay, now let's look at TPH vapor composition near two unweathered NAPL mixtures of gasoline and diesel. You can see that the vapor phase is predominantly comprised of low aliphatics, followed by low aromatics, and to a much lesser extent, medium aliphatics and aromatics, like jet A fuel and diesel. Why do the aliphatics dominate the vapor phase? The answer lies in two chemical partitioning properties, solubility limits and Henry's law constants. As stated a few slides ago, aromatics tend to have higher solubility limits, meaning they prefer to be in water. In addition, aliphatics tend to have higher Henry's law constants, which means they prefer to be in vapor instead of water. Here we present TPH fraction compositions of groundwater near NAPL, which again vary based on the oil, fuel, or NAPL mixture and weathering processes. By now, we know that aromatics are more soluble than aliphatics, and the most soluble hydrocarbon fractions are smaller or low aromatic hydrocarbons, followed by the smaller aliphatics, which are slightly soluble. If you compare overall solubility limits for gasoline versus diesel, you notice a much higher solubility limit for gasoline of 240,000 micrograms per liter, which is driven by the smaller, lighter aromatics. Compare this to diesel's 5,000 microgram per liter solubility limit, which is driven by medium aromatics, which are generally less soluble than small or low aromatics. Understanding TPH Fate and transport starts with identifying the TPH source mixture and weathering processes that may occur at your site. TPH can be chemically transformed in the environment, which is called environmental fate, and is driven by biological weathering, which changes the TPH composition while creating petroleum metabolites in the process. After TPH enters the environment, it can migrate from one medium to another, which is called environmental partitioning, ultimately ending up in an exposure media like groundwater or indoor air, where human and ecological receptors can come into contact with TPH. Therefore, identifying TPH fate and transport is essential in determining TPH risk. If you are interested in obtaining additional information on PVI, NAPL, or TPH, please visit the following ITRC websites, which contain links to both guidance documents and fact sheets.
The Interstate Technology and Regulatory Council is a nonprofit research program of the Environmental Council of the States. ITRC is a state-led organization composed of over 1,000 members from state agencies, federal government, tribal and international organizations, the private sector, academia, and community stakeholders. Members participate in technical teams which produce guidance, tools, resources, and training materials. If you'd like to be a part of ITRC, please visit the ITRC website at itrcweb.org. You can register for teams and learn more about how you can be an active member. ITRC's usage policy is available on the ITRC website. If you do plan to use ITRC materials, we ask you to review that policy in detail and be sure to credit ITRC. ITRC does not warranty the material nor endorse any specific products.